Well, thanks for joining me. We're going to do a little bit of review here. There's a practice quiz at the end that you can go through to check your understanding. And I just want to hit some of the big ideas in this chapter. Now, with nuclear stuff, sometimes you say nuclear energy and people think always negative things. They think of World War II and atom bombs and things like that. Well, after the war, scientists knew that nuclear had some great potential, and they wrote a letter to President Eisenhower at the time, and they developed a program called Atoms for Peace. And it was really to show that nuclear is not all evil. It has many good uses too. So I mentioned earlier about food irradiation, right? Like, which set of strawberries would you want to eat? The ones that have been irradiated on the right, or the ones that were left natural on the left? And I think most of us, if we understood that these were hit with high energy radiation with very short half-lives, by the time you eat it, the radiation's all gone. So I would prefer to eat the one on the right, personally. We mentioned cancer treatment. They can use seed crystals for prostate cancer, and different chemotherapies use radiation treatment. We have PET scans and CAT scans where you might have to drink different radioactive substances so that it shows up better as a dye in your body. We use it to destroy the anthrax bacteria. When it was mailed to members of Congress, probably 20 years ago, they would simply irradiate the entire mail truck before it was delivered to Congress. I believe even to this day that the mail delivered to Congress is irradiated before it goes. So if there's any radiation in it, any bacterial or viral threats, they will all be destroyed by the radiation. Another application of radiation is radiology, where you take a photographic film and you expose it with radiation, X-rays, and then you can look at to see if you have any broken bones in your hands or whatever the heck you're looking at that point. Okay? Maybe you have scoliosis like I do. This person, scoliosis is a curvature of the back. You can see it curving here. So they put in this, what's called a Milwaukee brace, a metal rod to try to straighten them out so they don't curve too much. And again, this is checking the correct alignment of that. Another good use of an X-ray. We mentioned those radioactive isotopes that you might drink, and maybe you're complaining of circulatory problems. So you drink this, and it goes in, and we can now see the individual veins in your body. It could be arteries around your heart or things like that. So they use them for medical diagnostic, abrasion studies and engines to see where things are. There's lots and lots of uses of radioisotopes in science. We had talked about that when you calculate a mass, it's an average atomic mass of the different isotopes. Some may be radioactive, some may be not radioactive. That's okay, right? It's just kind of reminding you of where isotopes fit into this whole discussion. All right, so here's the practice quiz, and I'll go through the questions, and then you'll want to pause before I go through the answer each time. Now, some of these are not necessarily like I'll give you, but they're good to just be thinking about. All right, so let's try it. Here we go. Which of the following is not an example of a spontaneous radioactive process? You'd want to hit the pause button at this point if you want to think about it. All right, so hopefully you recognized some of these terms. You recognized alpha decay as a type of spontaneous radioactive process. Beta decay, positron production, those are all obvious radioactive processes. Electron capture, it doesn't have to emit something, it can capture that. That's okay. Autoionization is not something we talked about. It's like where two water molecules maybe get together and produce a proton. It has nothing to do with this unit. And sometimes when you see questions, we foolishly pick the one that we've never heard of. That's not what you should be doing, right? The other ones you've heard of, and this one is the one we didn't hear of, that's maybe the one you want in this case. Let's try another one. If a nucleus captures an electron, describe how the atomic number will change. Again, pause the video, see what you come up with, and then check the answer. So here's the choices. Before I even look at the choices, I'm going to try to figure it out myself, right? So I've got some nucleus. This is not nitrogen, it's a nucleus here. And it's going to capture, absorb an electron. That's a beta particle, a 0, -1. Now, it doesn't really matter what element I make this. Maybe I will make it nitrogen, so it has an atomic mass. Well, if it has a number of 7 protons, it might have a mass of 14. So now I do the math. On the top, 14 plus 0 is 14. On the bottom, 7 plus -1 is 6. Element 6 is oxygen, and so this would be, element 6 is carbon, 8 is oxygen, 6 is carbon, and it has a mass of 14. So the question is, what will happen to the atomic number? Well, this is the mass. I'm not interested in that. This is the atomic number. It appears that it decreased by 1. So that is choice B. And so that's the one I'm going to pick, choice B. Let's try some more. Polonium is a naturally radioactive element decaying with the loss of an alpha particle. And what other particle? Again, pause if you need to. Adding this up, 84 is equal to 2 plus, well, 82 on the bottom. And then, there's the question, what's the second product? So it's an 82 on the bottom. And then on the top, 210 equals 4 plus 206. So I have to find, I know it's going to be one that weighs 206, so it's either lead or astatine. Well, element 82 happens to be lead, so it's going to be lead. Now, I've written out, see, this first one is an alpha absorption, but what we're told here is that it decays with the loss of an alpha. So it's not going to be this first example at all. Instead, it's going to be this one, where the polonium emits or loses an alpha and ends up forming a lead 206. Okay, so choice B. I see frequently students will sometimes get the alpha or whatever particle on the wrong side because they didn't read the question carefully. So read it carefully when you're doing these problems. Let's try another one. Thorium-234 undergoes beta particle production. What is the other product? Again, pause the video, work it out, and then come back when you're ready. So it says that thorium is produced. So I don't even care about the answers. I'm going to just try this on my own. So I'm producing, well, let me read that again. I misread it myself. Thorium undergoes beta particle production. So thorium produces a beta particle and something else. Now I've got it right. So look, 90 equals -1 plus 91. Element 91 is protactinium. And then on the top, 234 is 0 plus 234, so protactinium 234. How about choice A? And that is my answer. Got about 5 more of these for us to look at. The element curium can be produced by positive ion bombardment when an alpha particle collides with which of the following nuclei? Recall that a neutron is also a product of this bombardment. So curium can be produced. Well, that means curium's on the product side. So I'm going to draw an arrow, and it's curium with an atomic number of 96 and a mass of 242. And it is being produced. Okay? It's not reacting, it's being produced by the positive ion bombardment when an alpha particle combines with something else. So that means an alpha, a 4-2 with a 2 plus charge, is hitting something else. And then it says a neutron is also a product. So a neutron is a 1-0. So what I'm looking for is the missing piece right in here, the beginning. So looking at this, 96 plus 0 is the same as 2 plus 94. And on the top, 242 and 1 is 243. And I've got a 4, so I think I need a 239. And the element that has an atomic number of 94 is plutonium. So now I'm looking, is this a choice, plutonium 239? And sure enough, there it is, choice E. Kind of fun, actually, once you get to understand what you're doing. Let's try this one. When nitrogen-14 is bombarded by and absorbs a proton, a new nuclide is produced, plus an alpha. The nuclide produced is, again, let's write this out. Nitrogen-14 is bombarded by a proton. So that's on the reactant side. Nitrogen-14 is bombarded with hits a proton. Now, a proton is a 1-1. It has a mass of 1 and a charge of 1. And then it says a new nuclide is produced plus an alpha. So there's an arrow. We know there's something plus an alpha. And an alpha is a 4-2 with a 2 plus charge. So now the only thing we have to do is figure out what goes here. 7 and 1 is 8. 2 plus 6 is 8. Element 6 is carbon. On the top we got a 14 and a 1 is a 15. So 14 plus, well, in order to get 15, that's an 11. So how about the carbon 11 nuclide is what is produced. All right, 6 of these down, 4 to go. When the uranium-235 nucleus is struck with a neutron, the cesium-144 and strontium-90 nuclide are produced with some neutrons and electrons. Your job is to figure out how many neutrons are produced, how many electrons are produced. In order to do this, let's write out a balanced nuclear equation. So, to begin with, when the uranium-235 is struck with a neutron, so I've got uranium-235 being struck by a neutron. Remember, a neutron has a mass of 1, but no charge. It says then the cesium-144 and strontium-90 are produced. There's my cesium-144. Cesium's atomic number is 55, plus strontium-90. Strontium's atomic number is 38. Now, I'm told that I get at least some neutrons. A neutron is a 1-0, plus electrons, or an electron, that's a 0, -1. Now, what I did is I added this up. 235 plus 1 is 236. Then I added this up, 144 plus 90 plus 1, and I wasn't there. I needed one more, so I put a 2 here to make it work on the top. On the bottom, 92 plus 0, 92, 55 plus 38 plus -1 gives me the 92. So it appears as though we're going to produce 2 neutrons and 1 electron. So 2 neutrons, 1 electron, that's our answer. Let's try this one. When the palladium-106 nucleus is struck with an alpha particle, a proton is produced along with a new element. What is the new element? Read it carefully. Palladium-106 is struck with an alpha. That's on the reactant side. So there's our palladium-106, element 46, reacting with an alpha, and it says a proton, a 1,1p, is produced along with a new element. And if you simply add it up, 106 plus 4 is 110, 1 plus 109 is 110. On the bottom, 46 and 2 is 48, 1 plus 47, element 47 is silver. So the new element is silver that we're producing, specifically silver 109 is the isotope we're interested in. 2 to go. Here we are. Strontium-90 from radioactive fallout is a health threat because, like blank, it is incorporated into bone. Now, I won't even give you choices. If I said what elements make up a bone, you probably know the answer, right? Now, look at the choices that I give you here. Iodine, cesium, iron, calcium, and uranium. Now, I hope you picked calcium. It turns out that we're going to learn that both strontium and calcium are alkaline earth metals, and things that are in the same family, up and down, will tend to react similarly. And that's one of the reasons we're real concerned about strontium fallout from radioactive war or winter, because it's incorporated into your bones, and there it stays for a long time and does a lot of damage. Finally, our last question. Nuclear fusion uses heavy nuclides such as uranium-235 as fuel. False, right? Fission is the splitting of big heavy things like uranium-235 in nuclear reactors. Fusion is joining those light nuclides like hydrogens into helium. And that's what's happening on the sun. All right, there's no mass defect questions, so don't worry about any of that stuff. And that, you can see, is the end of the slideshow. I hope you're ready for your test tomorrow. I think you're going to do well. We can discuss in class just a couple little hints. Send me those emails if you have any questions. Take care. Bye-bye.